Okay, so as I said, reactions of aldehydes and ketones are two parts. Part number one is the one that we're discussing in these two chapters. Reactions at the alpha carbon, this is going to be chapter 23. So we're going to hold on to that until chapter 23. Reactions at the carbonyl, this means that we are reacting at the carbonyl. So the reaction is going to happen on the carbonyl, and your product will not have any carbonyl. No carbonyls. Your product will not show any carbonyl. Carbonyl will still be there, but whatever you're going to add is going to be on the carbonyl. So this is why we're going to call it reactions of carbonyls. We're going to talk about different reagents in there. The reaction is really simple. Very simple, and it's the same concept. The concept is the same. So once you know the concept of the reaction, you can use any nucleophile and then you can react it with the carbonyl. Now, whenever you're reacting with carbonyls or reacting on the carbonyl, the nucleophile on the carbonyl, the reaction can be either in presence of acidic medium or basic medium. Okay? So, first thing you have to consider the direction of polarization, as we talked about for the carbonyl before, and know what is the charge of your carbon, what's the charge of your oxygen. So the carbon is partial positive and the oxygen is partial negative. So let's say, for example, if I am working in a basic medium, this means that I am using a nucleophile in there. So this is the general mechanism in there. So if I am working with a basic medium, I am using a nucleophile in there with a negative charge. Let me have an example, like for example a CN minus, okay? So let's start with this, and we're doing sodium cyanide with sodium cyanide in there. So what is the CN? The CN is basically a carbon, triple bond, nitrogen with a lone pair and a negative charge. Okay, so this is your cyanide. What is that? This is basically a nucleophile. So the cyanide is a nucleophile because it has lone pairs and it has a negative charge. So it is a strong nucleophile in there. There is no sign that I have an acidic medium, so since it's a negative, then it is going to be a basic medium. Since it's a nucleophile and this carbon is partial positive, the oxygen is partial negative, then I know that the CN is going to come and attack the carbon. Okay? It's going to attack the carbon. Now, once you make a bond, you have to break a bond. You don't have an option. So you have to break a bond, and the double bond is going to, the electrons of the double bond, they're going to add to the lone pairs on the oxygen. So you're going to end up basically getting an oxygen. Now you are having two more lone pairs on the oxygen. Two more lone pairs on the oxygen. I'm going to keep my two CH3s, but see what I added in here? I added a carbon, triple bond, nitrogen. You can simply write it down as a CN. It's okay, it's fine. So we're going to have this now. The charge of the oxygen is negative. Oxygen with one bond is a negative charge. So this means that with this reaction, it's two steps. I need a second step. And my second step is basically any solvent that has a hydrogen, just to make, to protonate the oxygen and make it an OH. Normally, we avoid using an acid. We don't want to use an acid. It is a basic medium. So normally we use water, we use methanol. So any one of these solvents in there can do the job, and they can protonate the oxygen. So that oxygen in there is gonna basically take a hydrogen, and then we're gonna have an OH in here. Last time we said OH is a very bad leaving group, except if whenever you are doing a protonation. If you are doing protonation with water, then the OH minus can leave. The reason why the OH minus leaves here, because it can counter with the sodium, with the Na plus. So it can be a good leaving group in this case if there is a counter ion, if there's a positive counter ion to balance that. So this is an example of a nucleophilic addition on the carbonyl in presence of a basic medium. So if I'm having a basic medium, this is how the mechanism is going to go. A nucleophile, and again, the nucleophile is not necessarily a CN negative, just any nucleophile. It will attack the carbonyl if it's a basic medium in these steps in there. Now if I have an acidic medium, let's say if I have, for example, an HCN. If I have an HCN, now I know that HCN is an acid. It starts with a hydrogen, it is an acid. I know that the CN over here is my nucleophile, but it is basically connected to the hydrogen. I need to free it from the hydrogen so that it becomes a CN negative and it attacks the carbonyl. So this is why in the first step, I have to get rid of basically this hydrogen over here that is next to the cyanide, so that to free the CN, to make it a CN negative, and then once I make it a CN negative, once I make it a CN negative, then that CN negative can attack. It can attack, and I can get my product in this case. So the mechanism goes as follows. Remember, this is an acidic medium. If it's an acidic medium, you want to make sure in each step that your product is acidic. It cannot be basic, it doesn't make sense. If it's acidic medium, your product has to be an acid. Basic medium, your product has to be base. So the first step always with the acidic medium, you do have to protonate the oxygen. This is the difference, because I don't have a nucleophile to attack the carbon of the carbonyl. I have a hydrogen. So I want to protonate the oxygen. Now when I do that, see what I did over here? I freed the cyanide. I freed or the A minus in there. I just freed my conjugate phase. This undergoes resonance, and it's basically more stable when you have a positive charge on the carbon, which is less electronegative than having the positive charge on the oxygen. This is why we represent it like this. And then this structure over here is going to carry to the second step, and it's going to react basically with the H nucleophile. Now what I would do is, you have an option in here. What I would do is I would cut this basically, make it easier. So instead of using an H and U, I would go ahead and use the A minus right away. I would go ahead and use that right away. So this can come over here and attack, and I can skip this step here, and I can immediately get to my products. Okay, so skip that step and get to my product in there. You can either do this or you can work with the mechanism as written, but normally I'd like to take the A minus, attack it with the positive charge. See my arrows from the more to the less, from the nucleophile to the electrophile, and then simply you get your product. Chapter 18, we talked about Wolff-Kishner and Clemenson and reductions of carbonyls. Whenever they are on the benzene, you can simply reduce the carbonyl, not just on the benzene, you can reduce the carbonyls with Clemenson or Wolff-Kishner. Reduction is either changing the carbonyl into OHs, we're going to talk about this, or changing carbonyls into CH2s. If you use these reagents, you are changing the carbonyls into a CH2. So carbonyls basically are changed into two CH2s over, or a CH2, not two CH2s. So it's changed into a CH2 there. Wolff-Kishner works with a basic medium and with heat. We will come back to this reaction once we discuss the reactions of carboxylic acids, which is the carboxylic acid derivatives, which is chapter 23. We will come back to this reaction. So reduction of carbonyls, as I mentioned, it's two types. Either reducing carbonyls to CH2s by these two reagents, or reducing carbonyls into alcohols. Either one, okay? It depends on the agent that you are working with. So if you want carbonyls to be turned into CH2s, use either Clemenson or Wolff-Kushner. If you want the carbonyls to turn into alcohols, then in this case, you have to use either a strong or a weak reducing agent. Now in the lab we've talked about these reducing agents, and we call them reducing agents because we are adding hydrogens. This is what we are. We are adding hydrogens. Notice what we did over here. We took away the double bond and we added two hydrogens. You break the double bond and you form two sigma bonds in there. The reaction is really simple. There are three reducing agents that do this reaction. Either sodium borohydride, NaBH4. So either sodium borohydride, and this is the Lewis structure of the sodium borohydride. The boron is positive 3, and each of the hydrogens is a negative 1. So this is why the sum of all of this, the BH4, is negative. So this is why you need sodium to balance the negative charge. Same thing for the aluminum. The aluminum is basically positive 3. Each of these hydrogens is negative. This is a hydride. Hydride is an H minus. This is what a hydride is. This is a negative charge. Lithium hydride and this lithium aluminum hydride. Now lithium aluminum hydride is a stronger reducing agent than the sodium borohydride. Why is that? The reason why, because boron is more electronegative than aluminum. So boron, what it does, it's going to take the electron density from the hydrogen. So the hydrogen, which is the hydride in here, this is how I represent the hydride. So this hydride in there, is going to have less electron density around it. So this is why we're going to say that the hydride that results from the sodium borohydride is a weak reducing agent compared to the hydride that results from the lithium aluminum hydride. The hydride that comes from the lithium aluminum hydride has more electron density around it because aluminum is less electronegative. So it's not going to steal the electrons away from the hydrogen in there. So this is why this hydrogen that comes from the aluminum hydride, the lithium aluminum hydride, is a stronger reducing agent. Boron and aluminum are both metals, right? So this is why I am representing them as a metal. M stands for a metal and then a hydrogen in there. And the metal and the hydrogen is represented by a hydride, and this is how we represent the hydride. We're going to keep the mechanism really simple, really simple. One thing that I want to say in here, sodium borohydride normally is dissolved in either methanol or water. Lithium aluminum hydride is always dissolved in water. So the solvent for sodium borohydride can be either water or methanol, either or. But the solvent for the lithium aluminum hydride is always water. Mechanism is really simple, very simple in there. And you are reducing the carbonyl. See that carbonyl? This is an aldehyde. Aldehydes are always reduced into a primary alcohols. Ketones are reduced into a secondary alcohol. The reducing agent can either be sodium borohydride or lithium aluminum hydride. Now the lithium aluminum hydride is 2 steps, as you can see. It is 2 steps. The sodium borohydride is 1 step. This guy is 1 step here. And the solvent, methanol, is a solvent. We can use water instead. Any solvent that has a hydrogen will do the job. Any solvent that has a hydrogen will do the job. Let me write the mechanism for the reaction. It's really simple. Now you see it over there. I'm going to write it in an easier way. We are starting with a CH3 carbonyl. Okay, we're starting with the aldehyde, and we are reacting this with sodium borohydride. Now for the sodium borohydride or the lithium aluminum hydride, both they are going to give a hydride, which is an H negative. So instead of writing the sodium borohydride or the aluminum hydride like I have in here, okay, like I have in here, instead of writing it like this, you can simply write it as a hydride, a hydrogen with a negative charge. And this represents the hydride that comes out of either one of these hydrides, the lithium or the sodium borohydride. So we're going to start over here with the hydride. Since this is a nucleophile, nucleophile is going to be a basic medium, of course, because it's a nucleophile in there with a negative charge. So it's going to come immediately and attack the carbon, and it's going to form a negative charge on the oxygen. See how easy that is? Okay, so when it does that, see what I formed over here? I'm forming a CH3. Now, this is going to be an O. I already have 2 lone pairs on the oxygen. My double bond, when it broke, it added 1 more lone pair on the oxygen. Here you go. Of course, I still have the hydrogen in here. And see what I added? I added a hydrogen in there. This is the hydrogen of the hydride. This is the hydrogen that added. Of course, I will have a negative charge on the oxygen. And this is why I need a solvent. This is why I need a solvent. So you're going to have a solvent in there, and your solvent is going to be any solvent that has a hydrogen. Methanol can be one of them. Water can be another. So the solvent in there is going to come, see my arrow, from the oxygen to the hydrogen, because this hydrogen is partial positive. So from the oxygen to the hydrogen, and all of this is going to leave. And I'm going to end up having my CH3, my carbon, my OH. This is how I get my alcohol from the carbonyl. It's called reduction. And then I'm having a hydrogen and the hydrogen in there. Notice if I start with aldehydes, I'm going to get a primary alcohol. If I start with aldehyde, I'm going to get a primary alcohol. Now, of course, you're going to have your counter ion. In this case, I am not writing the other organic product. We don't need that, but if you want to write it down, I have my CH3, O negative, that is going to balance, of course, my sodium from the sodium borohydride. Okay, but you don't have to write it, since this is an electrolyte. You don't have to write that. So aldehydes, they get reduced into primary alcohols. You can try that same mechanism with ketones. Lithium aluminum hydride, the same thing. They do generate a hydride with a negative charge. So this is going to come, it's going to attack the carbon. It's going to form a negative charge on the oxygen. In the second step, the negative charge gets protonated from the water. Please try that. And you're going to form a secondary alcohol. So if you have if you want to get a secondary alcohol, you need to start with a ketone. If you want to get a primary alcohol, you have to start with an aldehyde. And then we have hydrogen in presence of PDC. This is a third agent for reduction of carbonyls. This is just you are adding 2 hydrogens. This is what you are doing. You're adding hydrogens in there. One hydrogen goes to the carbon, the other one goes to the oxygen. And you're going to end up having from the aldehyde will be reduced into a primary alcohol. And ketones, they will be reduced into a secondary alcohol. So all I did over here is I added a hydrogen on this carbon. This is what I did. I added a hydrogen on this carbon and the hydrogen on this oxygen. When you add 2 sigma bonds, you need to break the double bond. So you no longer will have a carbonyl in your product. If you have a compound that has both carbonyls and double bonds, so let's have an example in here. This is a compound, it has a carbonyl and a double bond. And you know that whenever you're working with hydrogen in presence of PDC, this is a simple addition, hydrogenation of the double bond. You're adding hydrogens to the double bond, remember that. Okay, so if you are adding hydrogen in presence of PDC, the priority is for the double bond, for the alkene. This is the priority, not the carbonyl. So one equivalence of hydrogen in presence of PDC is going to basically hydrogenate the double bond. It's going to add two hydrogens, and you're going to go from the alkene to the alkane. If you have an excess of hydrogen in presence of PDC, then basically you are reducing the carbonyl into a primary alcohol, into a secondary alcohol, in this case, since this is a ketone, and you are hydrogenating the double bond at the same time. Sodium borohydride or lithium aluminum hydride in presence of water. Add water, please. In presence of water, this only acts on the carbonyl, just the carbonyl. So it's going to reduce just the carbonyl into an alcohol. It's going to do nothing to the double bond. With respect to the strength of the reducing agent, lithium aluminum hydride is very strong reducing agent. Sometimes we want to decrease the strength of the lithium aluminum hydride. So in order to do this, what we do is we replace some of its hydrogens. Lithium aluminum hydride has 4 of them. Okay, we replace almost all of them except one with a bulky group. Like for example here, see all of the three hydrogens, I am replacing them with a tertiary butoxy group, and I left only one hydrogen. I only left one hydrogen in there, and that hydrogen is going to turn into a hydride. So this means that your lithium aluminum hydride will not keep reacting over and over and over again, because it only has one hydride. It doesn't have now 4 of them. It has only one. This compound is called lithium tritertiary butoxy aluminum hydride, and this is how normally we abbreviate it, and this is how you're going to see it in the reaction. Another mild, so these are called mild reducing agents. They are mild reducing agents. Another mild reducing agent is diisobutyl aluminum hydride, the DIBAL and the hydrogen in there. This is a diisobutyl aluminum. Al stands for the aluminum, and then H stands for the hydride. This is the diisobutyl in there. This is the diisobutyl in here. This is an isobutyl, and this is another isobutyl group. So I replace 2 of the hydrogens with an isobutyl, and I'm left with only one hydride. Just one hydride. I don't need more than that. Why do I need these reagents in there? Why do I need to make the lithium aluminum hydride mild instead of strong? The reason why, when I am working with esters, when I am working with acid chlorides, then I would need to limit the reduction. Sometimes you want to limit the reduction and you want to get an aldehyde instead of an alcohol. So this is why you have to basically decrease the strength of the reducing agent and make it mild. I'll show you some examples, okay? So the mild reducing agent normally we use whenever we are reducing acid chlorides and we are reducing esters. If we want aldehyde to be our product, then we have to use a mild reducing agent. If we want to go to form a primary alcohol, then we use the strong reducing agent, like we use the lithium aluminum hydride in there. By the way, sodium borohydride, NaBH4, does not reduce the derivatives of carboxylic acid. So it doesn't reduce the acid chloride and it doesn't reduce the ester. What reduces those two is just the lithium aluminum hydride. So the strong reducing agent that I'm talking about here to form the primary alcohol is just the lithium aluminum hydride only, no sodium borohydride. Okay? So let me put this here with NaBH4 in presence of methanol. You have no reaction. Whether you start with an acid chloride or you start with an ester, any one of those with sodium borohydride, there is no reaction. So the question is, if you use a strong reducing agent or a mild reducing agent. If you use a strong reducing agent, then your product is going to be a primary alcohol. You're going to reduce all the way. If you use a mild reducing agent, then you're going to basically stop at the intermediate, which is the aldehyde. We're going to do the same thing for the esters. Esters also the same thing. You can use a strong reducing agent, go straight to the alcohol, or a mild reducing agent, and then you're going to go to the aldehyde. So either one of those. The mechanism is really easy. Here I am using the strong reducing agent. So see, I did not replace the hydrogens with a bulky group. So I'm using a strong reducing agent in this case. So let's basically represent this whole thing as a hydride. And remember, you have 4 of them. You have 4 of them, so you can keep using them. As long as you create a carbonyl, you can keep using them. So we're going to start with the mechanism in here for this reaction. So with the mechanism of this reaction, let's see. Okay. Here you go. So okay, we're having our hydride. So the hydride is our nucleophile, right? So this nucleophile is going to attack the carbon of the carbonyl and form a negative charge on the oxygen. And when it does, you're going to form a negative charge on the oxygen there. Of course, the lone pairs, don't forget. I added the hydrogen. I added the hydrogen here. And then I'm forming my O and then my methyl group in there, right? Now what do you think is going to happen over here? You do have a very good leaving group. See that leaving group, that good leaving group over there? Do you see it? This is a very good leaving group. It can easily leave if I do a simple resonance in this case. So I do a resonance in here, kick out all of this group. This group is going to leave. Normally, esters and acid chlorides, they do have good leaving groups in these types of reactions. Okay, and then after this leaves, then what I'm going to end up having is basically an aldehyde. Notice I am back to the carbonyl again. The rule says I can keep using the hydrogen of the lithium aluminum hydride. I can keep using it as long as I have it. I can keep using it as long as I have a carbonyl in there, because this is its job. Its job is to reduce the carbonyl into an alcohol. So my second lithium aluminum hydride in here, my second hydride that is coming from the lithium aluminum hydride is here. Okay, so we're going to use another lithium aluminum hydride, another hydride in there. This is going to come, it's going to attack the carbon, it's going to form a negative charge. This is going to form a negative charge in there. Now once it forms a negative charge, now notice here I'm going to have the 2 hydrogens. This is the second hydrogen in there. I'm done. I don't have any carbonyl anymore. So once you don't have any carbonyl anymore, now it's the time in order to protonate. So we're going to use the water. Whatever solvent you have. Lithium aluminum hydride normally uses water. So now this is going to come, take the hydrogen, all of this is going to leave. And you're going to end up basically getting your product in this case. I'm just going to write the product all the way to the top there. I write it in blue. So your product is going to be basically an OH and then a hydrogen in the hydrogen. Notice I went from an ester to a primary alcohol whenever I use the strong reducing agent.